So the next part of the number system is signed binary number system. The numbers in general, maybe the number may be positive or the number may be negative. Whether the number is a decimal number or binary number or hexadecimal number or octal number, in general, if at all we are talking, the numbers are possible, maybe the positive sign or maybe negative sign. In concern to the digital circuits, if at all looking, in concern to the digital circuit, we are dealing with the binary numbers. So the binary numbers are also having maybe positive sign or maybe negative sign. Any sort of information in the digital circuit, any sort of information in the digital circuit is represented using only the binary bits, maybe binary bit 1 or zeros. So when we are talking on these binary numbers, the given binary number is a positive number or the given binary number is a negative number, this sort of information also we must indicate only by using binary bit or by using binary bits. Suppose we are having a register with the size of n bits. Let us consider the register is the size of n bits. The register is nothing but a storage device. The register is basically a storage device to store binary number. When the register is the size of n bits, one bit, particularly this most significant bit, is reserved for the sign bit purpose. One bit, that is the most significant bit, is reserved for the sign information purpose. And the remaining bits are concerned related with the magnitude. The remaining bits are concerned related with the magnitude. When we are looking to these signed binary number systems, we are having three standard notations. One notation is sign magnitude number system. Signed ones complement notation. Signed two's complement notation. These are the three standard notations we are having on the binary numbers. In all these representations, whenever the most significant bit is 0, in all these representations, whenever the most significant bit is 0, the number is positive. Whenever the most significant bit is 1, the number is negative. In all these notations, this is a common rule. When the most significant bit is 0, the number is positive. When the most significant bit is 1, the number is negative. And the remaining bits are giving information about the magnitude. The wording what I am using, listen well. I am not talking the remaining bits are equivalent to magnitude. Such wording I am not using. I said the remaining bits are concerned for magnitude. So what way they are differ? These three notations, what way they are differ? The differ will be looking as far as the negative number representation is concerned. The differ in all these notations, we are not having anything with the positive numbers. But with respect to the negative number representation is concerned, in all the three notations, we are having a difference. We are having a difference. So let us look first about this sign magnitude. In the sign magnitude representation, whether the number is a positive number or the number is a negative number, the magnitude is always true magnitude. The magnitude is always true magnitude. So that we took an example, the registry is the size of n bits. In that case, after reserving MSB bit, that is Rn minus 1 to M sign bit, the remaining bits Rn minus 2 to R0 are directly giving the magnitude value, whether the number is a positive or negative. The remaining bits are giving directly the magnitude value. Coming to sign 1's complement. The sign 1's complement, if the number is positive, the remaining bits other than MSB, the remaining bit means the remaining bits are giving true magnitude. Remaining bits are giving true magnitude of the number. When the number is negative, the magnitude is in 1's complement form. The magnitude is in 1's complement form. So whenever the number is negative, the magnitude is not true magnitude, the magnitude is in 1's complement form. In the case of this sign 2's complement notation, when the number is positive, the magnitude is a true magnitude. When the number is negative, the magnitude is in 2's complement form. Magnitude is in 2's complement form. So, as I said already, in all these three notations, we are having a difference as far as the negative numbers are concerned. There is no difference as far as the positive numbers are concerned. In the positive numbers representation in all the three notations, it is same. Positive number representation in all the three notations, it is same. They are having the magnitude is always true magnitude. But whenever the number is negative, the magnitude is a true magnitude for sign magnitude notation. The magnitude is a true magnitude in the sign magnitude notation. But in the sign 1's complement, in the sign 2's complement, the magnitude is not a true magnitude. In sign 1's complement notation, the magnitude is in 1's complement form. In the sign 2's complement notation, the magnitude is in 2's complement form. So, with respect to these negative numbers, we are having the difference. The difference we are having only with respect to negative numbers. Let's try a question. Note down. The register R1, R2, R3 content is given below. The register R1, R2, R3 content is given below. The register R1, R2 content is given below. What is equivalent decimal values? Sorry, what are equivalent decimal values? What are the equivalent decimal values? in the register R1, R2 and R3, in the register R1, R2 and R3, in the register R1, R2, R3, if a bit, the data is, if the data is in sign magnitude representation, the data is in sign magnitude representation. B bit, if the data is signed ones complement notation, the data is signed ones complement notation. C bit, the data is signed two's complement notation, if the data is signed two's complement notation. So question I am repeating. The register R1, R2, R3 data is shown below. What are the equivalent decimal values in the registers R1, R2, R3 if A bit, the stored data is in sign magnitude representation, if the stored data is in sign magnitude representation. B bit, if stored data is in sign one's complement notation. C bit, the stored data is in sign two's complement notation. It is a question. So take some time and you try. So question is very straightforward, very simple question. These are the three registers, some content I mentioned the registers. We are taking here a question. First case, assuming the data which is stored in the register R1, R2, R3 are in sign magnitude, that is one case. And in the second case, sign 1's complement, sign 2's complement. We are interested to know what are the respective equivalent decimal values for each case. What are the respective equivalent decimal values in each case? That is the one which is interested for us. So coming to the A bit, the stored data is in sign magnitude. So once the stored data is sign magnitude, the magnitude is, whether the number is positive or the number is negative, the magnitude is only in true magnitude form. Magnitude is only in true magnitude form, whether number is positive or negative. Hence, the register R1 MSB bit is 0, so the number is positive. The number is positive. And the magnitude is a true magnitude. The magnitude, if you read, it is 11. The magnitude, if you read, it is 11. So plus 11. The register R2 MSB bit is 1. So the stored number is negative. The magnitude is true magnitude. Hence, it is minus 11. In the register R3, MSB bit is 1. Hence, the number is negative. The magnitude is a true magnitude. A bit we are dealing. So, it is 6. These are the decimal equivalent value respectively from register R1 to R3, considering the stored data is in sign magnitude notation. The stored data is sign magnitude notation, considering. Similarly, sign 1's complement notation, if you look, the positive number is concerned, register R1 data is a positive number. The positive number is concerned in all the three notations, it is same true magnitude. So it is plus 11. For register R2, the number is negative, but the magnitude is not true magnitude. The magnitude is in 1's complement form. The magnitude is in 1's complement form. The number what we are having is here 11011. It is a number. So this register R2 number MSB is 1. So we are deciding first the number is negative. Later, to read the magnitude of the number, we need to perform the complement operation on the total content of the register. It is a practice you need to make. Even system point of view, if you look, the compiler will do the same job. And hardware, whenever you are building, the hardware also will do the same sort of work. While looking to the MSB bit, we'll be knowing whether the number is a positive or negative. After deciding the number is a positive or negative, to identify the magnitude, we are performing complement operation on the total content of the register. While performing complement operation on the total content of the register, we are reading here the decimal value is 4. Along with the sign bit, it is a minus 4. Along the sign bit, it is a minus 4. Similarly, the register R2, if you look, the number, register R3. Similarly, if you look to the register R3, the number is here 10110, 10110. So the number is negative because MSB bit is 1. To read the magnitude, we are performing complement operation on the total content of the register. While performing complement operation on the total content of the register, the magnitude we are reading as 9. Along the sign bit, it is minus 9. Along the sign bit, it is minus 9. Similarly, if assuming the stored data is in sign 2's complement notation, the register R1 is concerned no change because the number is positive. The remaining bits in general we said Rn minus 2 R0 are referring to only true magnitude. Hence it is only plus 11. Coming to the register R2 and R3, the stored numbers are negative. So the magnitude is not true magnitude. The magnitude is in 2's complement form. Magnitude is in 2's complement form. So here also the work is same. As and when work is same with respect to 1's complement I am talking. So as and when we are having the sign bit is 1, the number is negative, and to read the magnitude of the number, we need to perform the 2's complement operation, the total content of the register. We need to perform the 2's complement operation, the total content of the register. So when we are performing the 2's complement operation, the total content of the register, conventionally, if we try, we are looking first 1's complement. 1's complement we are reading as this. Later, we are performing add 1 to the rightmost digit in general. In this case, binary number system rightmost bit. Hence, we are looking here. This is 10100. So from this, we are recognizing the magnitude is 5. Along the sign bit, we are talking it is minus 5. Along the sign bit, we are speaking it is minus 5. When we are dealing with these 2's complements, when we are dealing with the 2's complement, to read the 2's complement of the number, instead of going such a conventional way, we can think little alternatively. Little alternatively, what is possible is scan the number from right to left. Scan the number right to left. And we are keeping the bits as it is. In general, I am talking. We are keeping the bits as it is until we are not reading first bit is 1. After reading first bit is 1, of course, it has happened in this case only this LSB itself. We are performing bitwise complement. While performing bitwise complement, effectively this is your 2's complement, what we are having conventionally. So it is useful whether LSB is 1 or LSB is 0 also. So what is the work we are having is, we are having a work as we are reading the bits as it is until we are not reading first bit as a 1. Once we are reading first bit is a 1, we are performing bitwise complement. Then it becomes the 2's complement. So to look some other example, I am having a binary number something like this 10110 100 suppose. For this binary number or on this number, if you want to perform the 2's complement operation, based on the discussion what I am talking, what we supposed to do is where we must read the bits as it is until we are not reading the first bit is 1. We are scanning the bits right to left, that is LSB to MSB. We are reading the bits as it is until we are not reading first bit is 1. The scanning is not from left to right, it is from right to left, from LSB to MSB. We are reading the bits as it is until we are not reading the first bit is 1. As and when we are reading the first bit is 1, next bit onwards, we are performing bitwise complement. Hence, so this is the 2's complement. You can make a cross check with the conventional work. Conventional work, if you look to the cross check, we are reading first 1's complement. So 1's complement of this number we are having as and 2's complement of this number we are reading while adding 1 to the rightmost digit in general. Here in this case rightmost bit. So while adding 1 here, it is 0, it is 0, it is 1, it is 1, 0, 0, 1, 0. So it's the one what we are having. It is one and same. Hence, in particular I am talking, whenever the given binary number is to more number of bits, whenever the given binary number is more number of bits, so going such a conventional way, 1's complement plus 1, I suggest better you try to work like this. Read the bits from LSB to MSB. Scan the bits from LSB to MSB. Read the bits as it is until we are not reading the first bit is 1. Once we are reading first bit is 1, later perform bitwise complement. It's the best approach. It is a shortcut. It will take less time. And of course, it is more useful whenever the number is with more number of bits. The given number is the 3 bits, 4 bits. There is no fun to use this. So anyway, coming to this question. Here we are having it is a minus 5. Similarly, the register R3, we are having MSB bit is 1, so number is negative. The magnitude is not true magnitude. The magnitude is in 2's complement form. To read the true magnitude, we need to perform the 2's complement operation on the total content of the register. The wording what I am using, note well. Whether it is a 1's complement case, whether it is a 2's complement case, once the number is negative, to read the true magnitude, after identifying the sign, we are performing complement operation on the total content of the register. So, while performing 2's complement here, we are scanning the number from LSB to MSB, right to left. We are reading the bits as it is until we are not reading the first bit is 1. After reading the first bit is 1, we are performing bitwise complement. So, while performing bitwise complement, we are having this magnitude is 10. Along with the sign bit, it is minus 10. Along with the sign bit, it is minus 10. So, these are the answers for the question what we mentioned. The question what we said is, 3 registers are having so and so data. The stored data is sign magnitude, stored data is 1's complement form, or stored data is in sign 2's complement form. What are the respective equivalent decimal values? It is a question we considered. So on this question, they are having, these are the answers. On this signed binary number system, another important point is the range of the numbers. The another important point is the range of the numbers. in sign magnitude representation, the range of the number. Range is talking about what is the lowest decimal number we can represent, what is the highest decimal number we can represent. That is coming to be range. So, if you look to the sign magnitude representation. In the sign magnitude representation, the range is minus to the power of n minus 1 minus of 1 to plus to the power of n minus 1 minus of 1. A sign in the sign 1's complement notation, minus of to the power of n minus 1 minus of 1 to plus to the power of n minus 1 minus of 1. In sign 2's complement notation, the range is minus of to the power of n minus 1 to plus to the power of n minus 1 minus of 1. So this is the range of the numbers. Suppose we are having the register size, for example, is 4. If the register size is 4, the range, if you speak in the sign magnitude notation, the range is minus 7 to plus 7. So one bit is reserved for the sign. The remaining bits are for magnitude purpose. Hence, whenever n is 4, 4 minus 1, 3. So to the power of 3, that is 8 minus 1 minus 7. 2 plus to the power of n minus 1 minus 1. So that plus 7. So if we look like this, here also, of course, minus 7 to plus 7. Here it will be minus 8 to plus 7. In the case of the 2's complement, it is minus 8 to plus 7. So we are understanding the sign 2's complement notation, we are accommodating one negative number more. In other way, the range in sign 2's complement notation is more comparing with the sign magnitude or sign 1's complement notation. The range is more. Just give a thought. How it is happening so? How we are looking the range as more in this sign 2's complement notation comparing with the other two cases? Just give a thought process. How this is coming to be true. So you might be identified how it is the range. To understand how it is the range, we need to do little work. We need to do little paperwork. Let us consider an example of the 4-bit case. The register bits R3, R2, R1, R0. On this 4-bit or in this 4-bit register, the possible values, if you look here, binary format, we are looking, there are 16 possible combinations. So these are the 16 possible combinations on 4-bit register. Now consider the stored data is in sign magnitude representation. The stored data, let us assume, is in sign magnitude notation. Once it is sign magnitude notation, as usual, the MSB is result for the sign bit. So MSB bit is talking about the sign information. For these first 8 combinations, we are looking MSB is 0, so number is positive. Hence, we are looking here plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. I think one is missing here. 0, 1, 1, 1. So until to this, we have to talk. First 8 combination, number is positive. So plus 7. For the remaining 8 combinations, the sign bit is 1. So number is negative. This is plus, this is minus 0. It is minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. Let us consider the stored number is sign 1's complement notation. If the stored number is in sign 1's complement notation, as usual for the first 8 combination, the number is positive because of sign bit is 0. So quickly you can read here plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. For the remaining 8 combination, the sign bit is 1, the number is negative. Hence, we are looking here. It is minus 7. It is a minus 7. This is minus 6, minus 5, minus 4, minus 3, minus 2, minus 1. It is a minus 0. It is minus 0. The last case, sign 2's complement notation. So as usual for the first 8 combinations, plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. For the remaining 8 combinations, the number is negative. Hence, the magnitude is not true magnitude. The magnitude is in 2's complement form. If you look here, 1, 0, 0, 0, this is minus 8. So the number is 1, 0, 0, 0. While looking to the sign bit, we are having this as negative number. To read the true magnitude, what we said is we need to perform the 2's complement operation on the total content of the register. While performing the 2's complement operation on the total content of the register, it is a 2's complement for this number. As I said, we are reading the bits as it is until we are not reading the first bit is 1. So it's the first bit we are reading 1. So until to that we are reading as it is. Later we are reading the magnitude from this work. The magnitude is 8. Along the sign bit we are speaking it is minus 8. Along the sign bit we are speaking it is minus 8. So the next one is minus 7. Here minus 6. It is minus 5. Minus 4. Minus 3. Minus 2. Minus 1. So the range in the sign 2's complement number system is minus 8 to plus 7, assuming the number is the size of 4 bits. For general case, n-bit case, the range is minus of 2 to the power of n minus 1 to plus 2 to the power of n minus 1 minus of 1. And other two cases, of course, it is minus 7 to plus 7. And other specific observation we are having. With the sign magnitude and sign 1's complement notation, The binary 0 is not having unique representation. The binary 0 is not having unique representation. In sign magnitude notation, the binary 0 we are having with the meaning of plus 0 and minus 0. In sign 1's complement also we are looking binary 0 representation with plus 0 and minus 0. Whereas in the sign 2's complement it is not the situation. In the sign 2's complement we are having the binary 0 representation. It is a unique representation. It is only unique representation. The binary 0 representation is concerned on the number axis. It is the origin point. It is the origin point. Basically, there is no means of the negative 0. There is no means of the negative 0. It is the origin point. But we are looking the sign 1's complement and also in sign magnitude. There is a conflict in the sign magnitude as well as sign 1's complement notation. There is a conflict. The conflict what we are having is we are having the number with the means of plus 0 and minus 0. It is a conflict we are having. That is not the case with the sign 2's complement notation. In fact, we are having binary 0 representation as a unique representation. It is one of the reasons why wherever we need the complements, particularly as I said in the introduction part of these complements, wherever we need these complements, particularly for subtraction only we are using. So we are having the usage of only sign 2's complement notation. The reason to prefer sign 2's complement procedure or sign 2's complement notation comparing with the other two procedures is in the sign 2's complement notation the binary 0 is having unique representation. Binary 0 is having unique representation in sign 2's complement notation. It is a reason, it is one of the reason we are preferring the sign 2's complement notation wherever we need the complements. So better you make a note as the binary 0 is having unique representation. Binary 0 is having unique representation binary 0 is having unique representation in sign 2's complement notation. In sign 2's complement notation. In sign 2's complement notation. Binary 0 is having unique representation in sign 2's complement notation, whereas binary 0 is not having unique representation in sign magnitude or sign 1's complement notation. As I said already, it is one of the reasons to prefer this 2's complement wherever we need the subtraction operation. So there is one more reason we'll talk while developing the hardware for the subtractor circuits. Just open the workbook. Look to the try yourself question, the chapter 1. One of the question, let us try. So open the workbook, look to chapter 1. Try yourself question. One of the question, it was a question in 2016 GATE exam CS paper only. The question number is T12. Of course, for try yourself, I given in the workbook the key is available. But that is not the case. We have to check how the answer is so. How the answer is so. Here the question what we are having is, if you want page number is 47. Chapter 1, number system is in chapter 1. So the question what we are having is, let x be the number of distinct 16-bit integers in 2's complement representation. So we are having here 16-bit data. It is mentioned x be the number of distinct 16-bit integer in 2's complement notation. Okay. Let y be the number of distinct 16-bit integers in sign magnitude representation. It is sign magnitude representation. It is sign 2's complement representation. So there are x number of distinct integers in the sign 2's complement notation. There are, if this question, if you simulate on 4-bit, the data which is available on the board, for 4-bit case, how many number of distinct integers in sign 2's complement notation? If you see, if you count, they are having 16 distinct integers. N is 4, so that we are looking total, all combinations are used, all 16 combinations are used. So 2 to the power of 4, it is giving total number of distinct integers. If you come to the y are distinct integers in sign magnitude notation. The 16, if you look to the distinct integers in the sign magnitude notation, because of plus 0 minus 0, effectively only 0, we are having only 15 distinct integers. We are having here only 15 distinct integers. So here this is coming as 2 to the power of n minus 1. So it is 2 to the power of 4 minus 1, hence 15. The difference we are talking as per the question, x minus y difference is 1. Difference is 1. Whether it is a 4-bit or whether it is a 16-bit or whether it is a 10-bit or whether it is 8-bit, any case, on this question, the answer must be only 1. On this question, the answer must be only 1. We are having always in sign 2's complement notation, comparing with the sign magnitude or comparing with the sign 1's complement, we are having representation of 1 extra integer. So x minus y will be 1. Whether y we are talking maybe sign magnitude or maybe sign 1's complement, the answer is not changing. The answer is 1. So it was, as I said, it was a question in the 2016 GATE exam in the CS paper. Let's look little discussion on the 2's complement. Few other points, let's try to look. Suppose we are having a number bn minus 1, bn minus 2 and so on, b1, b0. Consider the given number is in sign 2's complement form. The given number is in the sign 2's complement form, let us assume. For this number, when the number is in the sign 2's complement notation, 2's complement form, for this number, if you are interested to look what is its equivalent decimal value, one of the simplest way we can look here as minus 2 to the power of n minus 1 bn minus 1 minus to the power of n minus 1 b n minus 1 plus to the power of n minus 2 b n minus 2 to the power of n minus 3 b n minus 3 and so on to the power of 1 b1 to the power of 0 b0. It is an equation possible to use. It is an equation which is possible to use. So effectively, if you look here, it is a polynomial equation. This polynomial equation effectively resulting to be some decimal value. Hence, we can look alternatively minus to the power of n minus 1 b n minus 1 plus the remaining bits, the equivalent decimal value. So if you work out like this, it is giving its equivalent decimal value. It is giving its equivalent decimal value. So of course, theoretically I mentioned, but let us try to check few examples. With a few examples, try to work out. Suppose consider we are having a number as 10101110. If this is a number, if this is a number, one zero one zero one one zero. The given number considered is in the 2's complement form. We are interested to look what is its equivalent decimal value. What is its equivalent decimal value? We are interested to know. So the work what I said based on this, you can see here. Here it is a B, I think 6. Total I think we are having here 7 bits. So B6, B5, B4, B3, B2, B1, B0. So based on this, the general formula what I said, minus to the power of n minus 1 is 6. N minus 1 is 6. Okay. So the notation what we are having here also same. Is extending subscript 0 to n minus 1. Same thing. 0 to n minus 1. N minus 1 is a 6. Plus, as a conventionally, if at all you are looking, you have to write this total polynomial equation. If you write the total polynomial equation, it is to the power of 5 into 0, to the power of 4 into 1, to the power of 3 into 0, to the power of 2 into 1, to the power of 1 into 1, to the power of 0 into 0. So this is minus 64. To the power of 6, it is a minus 64. And the remaining bits, if you look, this is 0. To the power of 4 is 16. It is 0. To the power of 2 is 4. To the power of 1 is 2. It is 0. So effectively what we are looking, 16 plus 4, it is 20 plus 2, 22. Hence, this is minus 64 plus 22. It is giving a decimal value as minus, I think 42. Minus 42. As I said, instead of going such a lengthy equation, in a simplest way, I said, once the number is a 2's complement form, we said minus to the power of n minus 1. So for that, what you have to do is, you have to count the number of bits which are right side of this MSB. So the number of bits right side of the MSB are we are looking as 6 bits. So n minus 1 is default, it is 6. So again, I am repeating this. When quickly you want to look, while avoiding all this, you can see here now, MSB bit is 1. N minus 1 you want to identify. Further purpose, how many number of bits we are having right side of the MSB, just count. So just scanning only we are able to speak, that is 6. So that minus 2 to the power of 6 plus the decimal equivalent value of this. The decimal equivalent value of this, if you are having little practice properly with the conversion of the binary to decimals, we are looking, this is 22. Hence, effectively, we are having this is minus 64 plus 22. So, answer for equivalent decimal value is same, minus 42. So, if you practice a little like this, is a shortcut, you can speak the answer little fast. The shortcut, you can speak the answer little fast like this. Suppose so this is minus 42. Suppose we are looking here the question, assuming the given number is a positive number. The given number is a positive number, suppose. Same rule, same procedure. So to read the equivalent decimal value, as I said, minus 2 to the power of number of bits right side of the MSB, so 6 bits into, in fact, into Bn minus 1. So into Bn minus 1. Earlier, Bn minus 1 was 1, so into 1, not mentioned, but it is a means. Here into 0. Into 0 is the one what we are having a general formula. And plus of the equivalent decimal value of the remaining bits. The remaining bits equivalent decimal value, if you read, it will be 18. I think, make a check well. 1, 2, 3, 4 to the power of 4, 16 plus 2, 18. Hence, effectively, this is nothing but plus 18. Effectively, it is nothing but plus 18. So, you can use this sort of thing on number, maybe with a positive sign or maybe negative sign. Maybe positive sign or maybe negative sign. This is possible for us to use. So, this sort of work we can do on the sign 2's complement notation. Whether sign 2's complement or 1's complement is not the issue, but don't mix now with 1's complement. Let us fix our discussion only on the 2's complement. So, when I am talking sign 2's complement, whether I am mentioning sign magnitude 2's complement or sign 2's complement, the meaning is same. Without using a word, the magnitude also, if I am talking sign 2's complement, default, it is a sign magnitude only. I am not using this word also, or sometimes the question papers will be looking, the given number is in, sorry, sometimes you will be having in the question papers, the given number is in 2's complement form. Sometimes you will be having in the questions as the given number is in 2's complement form. So whether it is mentioned the word sign magnitude totally or not, or simply if it is mentioned the word, sorry, whether it is mentioned as sign 2's complement or simply it is mentioned the word as in 2's complement, the meaning is same. I mean, without the word of the sign also, the meaning is same. Whether we are having the usage the word sign 2's complement or whether we are having the wording simply as it is in 2's complement, the meaning is same. Once the description we are having the 2's complement or 1's complement, default it is indicating only sign 2's complement or sign 1's complement respectively. And coming to the case, suppose I am talking a question as the given number, I am talking as given number is in 2's complement form and number is, say, something like this, and given number is in 2's complement form and number is this. given number is in 2's complement form and is this. If that is the case, what is its decimal value? If the question comes, default, we must write it is a plus 5. So don't try for complement operation. While look at the wording of the 2's complement, don't try for complement operation. I'm talking the given number is in 2's complement form and the number is this, means don't try to read the decimal value, its complement, nothing. Conversion of we are doing the 2's complement if and only the number is negative number. If the number is a positive number, no need to do any such complement operation. Be clear. No need to do any complement operation. So simply you have to look as it is as similar to the sign magnitude, nothing else. You have to look as similar to, as a sign magnitude. So this sort of care we need to take. So this again I am mentioning, whether it is mentioning sign 2's complement or it is mentioned simply as in 2's complement, default is indication always is a sign only. It is used, the same statement is valid even for the 1's complement case. So when I'm putting a question as the given numbers are in 2's complement form, what are the equivalent decimal values? When I'm talking the given numbers are in 2's complement form, what are the equivalent decimal values? We are using the same formula what I mentioned here for both the cases, whether it is a positive, whether it is a negative or positive, I'm using the same formula. Because the negative, we are having multiplication with, for clarity, I will write, we are having a multiplication with the 1. We are having the multiplication with the 1. But for a positive number, the multiplication will be 0. So that makes a sense. The answer is, of course, not matters whether the number is a positive or negative. Thus, formula what we mentioned, we are having possibility to use. So like this, quickly, the shortcut, we are having possibility to identify the equivalent decimal values. This work you can extend even for these things. Suppose I am having a question for the given decimal number, what is the 2's complement notation? What is the 2's complement notation for the given number? What is the 2's complement representation for the given number? So make a question, note down properly. I am putting here the question as, what is the 2's complement notation for the given number? Or what is the 2's complement for the given decimal number? What is the 2's complement for the given decimal? I'm not using intentionally the word sign. Whether I'm using a word sign or not, as I said, default sign needs to be taken into account with the complements. So if that is the case, while looking to this magnitude, we supposed to identify how many number of bits are required. How many number of bits are required. So while looking to this decimal value, we are looking for representing this, we are in need of minimum 4 bits. Because the 3 bits, we can go maximum plus 7. If we use the 4 bits, we can go up to plus 15. So we need 4 bits. Based on this, when I am writing this number, we need to look, if I speak, it is a MSB bit. Right side of this MSB bit, we need to have 4 bits. Right side of this MSB bits, we need to have 4 bits. We need to have 4 bits. And MSB bit, we are reading as a 1 because of this negative. Okay. And looking to this, we are looking, this is because of the 4 bits right side to the power of 4 minus, of course, into 1. Plus the remaining bits value must produce minus 11. So minus to the power of 4, we know it is 16. Of course, along the sign, minus 16. If I am putting here plus 5, the remaining bits I am making as a plus 5. Then minus 2 to the power of 4 plus 5 is minus 11. So 5 we are having while writing here, this is 0, 1, 0, 1. It is 0, 1, 0, 1. Hence, this is the representation in sign 2's complement notation for minus 11. If you are having a doubt, you can make a cross check. The number what I finally developed for this minus 11 is 10101. If you are having a doubt, you can make a check either maybe this or other procedure what I said. Because of MSB's one number is negative and we are performing 2's complement operation to read the magnitude, it is giving 10010. So if you are this 5, right? What I said, 16 minus 5, 11. Sorry. So 2's complement 1, it is 1010. So from this we are recognizing the magnitude is 11. Along the sign bit we are speaking, it is a minus 11. That is the one what I mentioned, the direct procedure. Or if at all we are using this sort of work, minus 2 to the power of right side of this MSB 4 bits, minus 2 to the power of 4 into 1 plus the magnitude of the remaining bits plus 5. Of course, minus 16 plus 5, this is minus 11. So if you use any one as per your convenient, you can practice as per convenient. So that practice will make you to use which is the best thing. So anyway, you can adapt the sort of procedure or conventional work, whatever the thing you feel comfort, you will feel convenient, or whatever the earlier practice you are having, use that. So anyway, the results are coming to be same. So this sort of procedure, this sort of work we are having possibility to use on this, particularly in 2's complement notations. Whether I am mentioning sign 2's complement or not, it is default sign 2's complement. This is all the things what we want to speak on the number system at this point. So the discussion what we did is how we are having a conversion of the number, which is in general we mentioned the radix of R1 to R2. Later we discussed the complements, 1's complement, 2's complement. Finally, the last topic what we considered in the number system is the binary signed binary number representation, signed binary number representation. It was the last topic what we discussed. So number system is concerned, at this point we are discussing only this. Even in the introduction also I said we are not discussing here the codes, that is gray code, BCD codes, we are not discussing. In the due course, while developing the hardware for the code conversions, there we'll be discussing the gray codes, BCD codes, accessory codes, all those things will be covering there. And also here I not discuss the binary arithmetic additions and subtractions, the additions and subtractions, that is arithmetic operations I not discussed here. Those arithmetic operations will be discussing in the due course while developing the hardware for additions and subtractions. As I said in the introduction also, if at all we are discussing as a part of the number system, wherever we need here, say for example for codes, while developing the hardware, while designing the hardware for code conversion, again repetition is required. Similarly, while building hardware for arithmetic operations, additions and subtractions, if at all we are discussing here arithmetic operations, again there we need to repeat. To avoid those repetitions, I am not discussing those things here. So the number system is concerned, these are the things what we want to discuss at this point. In the workbook, there are a number of different questions, good questions. Most of the questions may be from the previous GATE papers, and a few questions I given on my own. Try to solve those questions as many things as possible. Few questions I want to mention everybody to work out. The question chapter 1, of course, number system. Question number 1, page number if you want. 44. Question 1 you try, question 2, question 3, question 4, question 6, question 10, question 13. Many these questions, many, of course, few of the questions I may not be mentioning, all those questions also you can try. Question 18, question 32, I'm giving try yourself questions also, key anyway available, but try on your own how the answers are coming as true. So few of these questions try on your own as a homework, just I am mentioning, they are available in your workbook. Practice these questions. Anyway, in the due course, I will be discussing these questions in the class little later. Similarly, here I am giving some questions from chapter 2. They are related to the Boolean algebra. We already discussed. Question 4, page number 48. Question 8, page number 48. Question number 10. Question number 12. 49, page number. All these questions are chapter 1. Here, what I am mentioning, they are chapter 2. For clarity, the page numbers are given for more clarity. So all these questions are from the chapter 2. Try these questions also. What are the things we discussed in the Boolean algebra? with the knowledge of those things, we are having possibility to work on these questions. Okay, so we'll stop at this point.